Good morning. We're going to continue our video training series by looking at starting and stopping a motor. In our previous video, we've downloaded the APB software and got that installed on our computer. Now we're going to actually go in and write a small application. If we open up our package, the first thing we need to do is define a new project. In this case, we're going to use a 12 I/O point digitally powered unit with relay outputs. So we'll select this. And the first thing I'm going to do is expand out our screen. We only need one network or one page of program for this application. That will give us a bit better visibility. For the motor, we're going to need an output, obviously. So we'll put an output down, and if we right click it, we can go into the property box. We want to tie this to a physical output. Output 0 is as good as any. And we'll call this pump because my motor is actually going to be hooked up to a pumping system. We also obviously need some way of turning our motor on. So we'll put an input in, and we'll call this property start. And we're going to have some error detection or fault monitoring on our pump. So we'll put another input in, and we'll call this property no fault. Well, we need to make sure that we have both the start button and a no fault condition active to turn it on. So we need some combinatorial logic. Over here we see that we have a series of AND gates, OR gates, ability to complement a signal, exclusive ORs, and some more sophisticated combinatorial logic. In this case, we just need a simple AND gate. So we'll put an AND gate down. From a ladder logic point of view, think of an AND gate as a set of contacts in series. If you have 3 points, contact A, contact B, contact C, you'd need A and B and C on to turn on the output. An OR gate, conversely, would be a set of contacts in parallel. If contact A or if contact B or contact C was on, the output would be activated. We won't be using an OR gate. We've got an AND gate to satisfy our requirements. We'll connect our input. 2 inputs connected, and we'll connect an output. And we notice that we have an unused input. So let's go in and look quickly at the properties of the AND gate. We see that the input count can range from 3 up to 8. That means we can have up to 8 contacts in series for a particular AND gate. If we needed more than that, we just cascade AND gates together. Since we're not using this third input right now, we'll set it to a permanent high level because we want it on all the time. So we replace that. Now if we go into our simulation package, we see that we have no fault. We'll assume that. When we hit the start button, the pump comes on. When we hit the stop button, the pump goes off. It's about exactly what we'd expect it to do. Well, quite often the first thing we need to do is put in a latch, because we really want to latch our pump on and then be able to latch it off. So to do that, I'm going to delete this contact, go back to my digital I/O, and see that we have a series of timers, some push button functionality, blinkers, and then something called a reset set latch. That's exactly what we need to control the pump. We'll tie our input to the set pin. We'll tie our output to the pump. And we need some way to turn this off. So we'll go back to our I/O points, select the digital input, and connect it up to here. And we'll give this a name of stop. We don't need to give them names, but it makes it a little bit easier to understand what the application is supposed to be doing. Now when we hit our simulate button, we'll take it out of the fault condition. We'll hit start. we see that the pump immediately comes on. We turn off the start and hit the stop, and the pump immediately goes off. Now, if we hit start and then hit stop, leaving it on, we see that the pump immediately went off because the reset will always take precedence over the set on the latch, which is exactly what we wanted it to do. Well, the next thing we want to add in is some time delays. Quite often we want a time on and a time off delay. So we'll break this connection and we'll go down to digital I/O again, and we see that we have something called a time on off delay. Sounds like it may fit, so we'll slide one of these in, go in and look at its properties, and we see that we have a reset capability. We don't really need that right now, so we'll just leave that at permanent low level. We have an on time and an off time. We'll set our on time to say 3 seconds. We'll set our off time to 2 seconds. We'll connect our output through to the pump. We'll connect our input to the trigger. Run our simulator. Now we see that we have a preset 3 second on, 2 second off. This will be the current time. We'll take our pump out of the fault condition, hit start, see that it times up. After 3 seconds it turns on the pump. We'll hit the stop button, it times up, and after 2 seconds it turns the pump off. So we have our pump running. It has a nice timed on, timed off delay, got a set latch. And the last thing we want to do is change this fault handling. We said that this was a pump. We're going to assume that it's actually a submersible pump and that this is a CO detect input. Well, currently it's a digital input that's coming in. We're going to delete that one. And we're going to go back to our I/O types and see that we have an analog input. Well, CO detect is typically a resistance to ground, and it will drop below a certain threshold when we have a leak in the seal. We want that to be our condition that turns off, disables the pump. So if we go in and look at the properties on an analog input, first of all, since our digital input is using input 0.0, we want our analog to use input 0.1. And we'll call this CO input. And then we have to do something with our analog. Well, if we go into our analog section, we see that we have something called a analog threshold detect. And if we put one of these in and go in and look at its properties, we see that first of all there's the ability to apply a gain and an offset so we can linearize the signal somewhat. We have a reset, which again won't be used in this particular application. Then we have an on threshold and an off threshold. And the function will behave slightly differently depending on how we set these values. To try it out, we'll first of all set the on threshold to 5. And we'll set our off threshold to 7.5. We'll save that. We'll connect our analog input to the input and our digital output up to our AND gate. Now when we start the simulation, we see that we have a on threshold and an off threshold. When we click on our analog input now, we have a slider, so we can actually set the analog value. As I slide the analog input up, once it hits a value of 5, the output came on. If I continue sliding it up, when it hits a value of 7.5, it turned it off. So that isn't exactly what we want, since we're looking at a resistance to ground, which is going to change voltage. Let's stop this and go back to these properties. Let's set this one to 7.5. So it's going to turn on when it hits 7.5. And we'll set this to 5, which means it turns off when it drops below 5. Running our simulator again, activating our input. We see that When we hit 5, nothing happens. When we hit 7.5, it turns on. We can continue all the way up to 10. And then as we bring it back down again, once we hit 5, it turns it off again. So this gives us a input with hysteresis. It will, nominal value of on is 7.5, but if we get some noise on the line, it won't actually trip it off until it drops below 5. That's pretty much what we wanted for our threshold detect. So now if we set our input so it's valid, we hit start, we see our timer time's up, the pump turns on, we remove our start signal, we hit stop, it times down and turns the pump off. That pretty much completes our pump application. Please come back and see us again. You can visit us on the web at ingramproducts.com. And our next video, we will look at adding in a human interface to our pump controller to actually look at the pump conditions as the system's running. Thank you very much.